All right. Good afternoon, everyone. So I hope you all are doing well amidst the transport strike and the shift of the university to online learning. But anyway, for today, I decided to make a recording of the topic for today, which is LU factorization. I already gave you the module last time, or assigned it to you as a reading assignment, or at least for you to browse the module and see what are the basic concepts in linear algebra that you need to review in order to meaningfully participate in a discussion in not only for this module but also for succeeding modules, right? So essentially, as I mentioned last time, we will be looking at how to solve linear systems because linear systems really makes a good portion of the mathematical tools that are behind data science tools. And it's really important for us to get an understanding of how these processes take place at the background of every data science toolbox so that in the event that we need to modify or to make some adjustments to these algorithms, we'll be able to tweak that black box, so to speak, and make the process or the method more efficient or more suitable for our particular need. That's why I guess it's very important that, especially if you'll go to higher or to deeper data science, or if you want to develop your own data science tools, it's very important that you understand or at least have an idea about basic linear algebra or at least basic matrix theory, right? Now, as I mentioned in the introduction last time, it's very important that we know how to solve linear systems because essentially this can be used or this is being used in processing large amounts of data, like for instance, in making a big model of a natural phenomena, and you have to determine different types of parameters for your particular model. So you do data fitting, and usually this data fitting machineries will require us to solve large matrices. Actually, not just very large matrices, but matrices that are tall and slim, right? So you have much more rows than columns. And it would be an advantage for a data scientist or a mathematician or a statistician to have an idea how to formulate the particular problem and pose it to a computing device like a computer so that computers can efficiently and accurately solve these systems of equations, right? So we'll look at one particular way of or one particular efficient way of doing or solving lots of systems of equations, specifically the iterative ones, and that's via matrix factorizations. But before going there, let me just give you a quick recap of the basics of linear algebra or matrix theory that is involved in solving systems of equations. So, for instance, we are given the following equation. Oops, okay, let me use a pen. So, if you're given, say, 2x plus 5y plus 3z equals 1, 3x plus y minus 2z equals -1, and negative x plus 2y plus z equals 0. And we want to solve for the values of x, y, and z. Of course, your elementary algebra teacher taught you at least three ways on how to solve the system of equations. So you have elimination method, you have the substitution method, or you have Kramer's rule. But in linear algebra, what we usually try to do is to write it in terms of a matrix equation, right? Again, a matrix is just a rectangular arrangement of numbers, and we harvest the coefficients of the equations that we have here into a rectangular array or in a rectangular collection of numbers, right? So essentially, if I harvest it out, we can have a matrix A, which is what we call the coefficient matrix. So this would be 2, 5, 3. So that's going to be the first rows. The coefficients in the first row would be the first row of our matrix. And then we need to make sure that that the variables all lines up, right? So first column will be x's, second column will be composed of those with y's, and the third columns will be those with z's. Okay? So and then analogously, I'll have 3, 1, -2, -1, 2, and 1. This is essentially what we call the coefficient matrix. And it is said to be a 3 by 3 matrix because it has 3 rows and 3 columns, right? And then we have the matrix of unknowns, x, y, and z, right? We can call it by using the vector x. Let's put x bar just to distinguish it from the variable x here. And all the constants will come to the right-hand side of our matrix equation. So we'll have 1, -1, 0. And this is what we'll call, say, our vector b or b bar, right? So essentially, these two equations, so this system of equations and this matrix equation are equivalent, meaning one solution of one of them is also a solution to the other. But this presents a better form because it has a more compact representation that is more suitable for computers. So computers can easily store the values, the numbers or the coefficient matrix together with the constants, and it can perform what we will call elementary operations or basic arithmetical operations to this form or to the matrix equation form of our system. All right. Of course, this is a very textbook and a very simple example because we only have 3 rows, 3 columns representing an equation with a system with 3 equations and 3 unknowns. But in reality, the matrix A could be very huge. As I mentioned last time, I worked with matrices or with coefficient matrices of hundreds of thousands of rows versus hundreds of columns. And usually my computer will already complain about the size of that matrix, which cannot be handled by my RAM anymore, right? So, but essentially, this is the type of equations that we want to solve. So we want ax bar equals b bar, right? And want to solve for a. Of course, the as you have mentioned, or some of you mentioned last time, the classical solution here is x bar equals a inverse times b bar, right? Where a inverse is what we call the inverse of the matrix A, meaning what is to be multiplied to the matrix A, either to the, actually both to the left and to the right, so that we get the identity matrix. But again, we have identified some problems with this. Number one, we're not sure whether this matrix is invertible or not. And second, if it is invertible, matrix inversion is a very tedious process, not just for doing it by hand, but also in computer implementation, right? It's very expensive. So it's hard to compute the matrix of the inverse of a matrix using computers if the matrix is very large, or actually if the computer can compute it, it is very prone to computer errors or to machine errors or errors due to machine truncation because it's a highly unstable process. So aside from the expensive side of matrix inversion, there's also a question about stability, but we'll talk about that later. But essentially, this is the ideal solution if everything will fall into place, nice properties about the matrix A exist. But other than that, we need to discuss some other ways. And that's what we'll do in a couple of sessions. We'll talk about the more Penrose pseudo inverse. All right, but that's for later. So this is the ideal solution. But of course, again, we need to look for other ways on how to solve this system. Now, a popular method is what we call the Gaussian elimination method. The Gaussian elimination method, which I am confident you have met during your elementary algebra classes. But if you took linear algebra, we had the what we call this the Gauss Jordan algorithm, or the reduction of the matrix into a row echelon form. Right. So maybe I'll demonstrate that for those who took linear algebra, it's going to be a review. But for those who haven't taken linear algebra, it would be a new thing, right? But I guess if I remember it right, I have it in the slides later. But essentially, what we want to do is to form the augmented matrix. So essentially, the steps are you copy the matrix A and then augment to it the right-hand side vector B, right? So I'll have a matrix with one more column than the coefficient matrix, because I'll be augmenting the coefficient matrix with the matrix of constants. So I'm gonna have the original matrix A. So I'll just copy it. So matrix A. I'll copy that here, and then I'll append to it the the vector 1, -1, 0, which came from our constants over here. So I just copied it over. And the idea is to reduce this part, or the matrix A, into what we call an upper triangular matrix or a lower triangular matrix. The customary way of doing it is to reducing it to an upper triangular matrix. When we say an upper triangular matrix, it is a matrix whose non-zero entries only occur above the main diagonal. So if you have a huge matrix, this is your main diagonal. The main diagonal are the numbers sitting in the same row number as column number. So say elements of the diagonals are of the form numbers sitting at the ith row and the ith column. Essentially, the row number and the column number coincide with each other. And when we say upper triangular, so everything below the main diagonal is a 0, and non-zero entries may only occur above the main diagonal. So the only possible positions where non-zero entries will occur will be above the main diagonal or on the main diagonal, right? So this space here, we are free to put any number, but below the main diagonal, we should always have zeros. So that's an upper triangular matrix. On the other hand, a lower triangular matrix only allows non-zero numbers to be below the main diagonal. Everything above the main diagonal will be a 0. And we don't care about what's the number on the diagonal or below the main diagonal. Okay, so if it's clear, lower triangular and upper triangular matrix. And in our particular purpose, I will reduce this matrix, all right, or at least this part of the augmented matrix to an upper triangular matrix. So I want the numbers below the main diagonal to turn to zeros. And how will I do that? I will use elementary row operations, or EROs. So elementary row operations, we have three types of elementary row operations. So these are things that we do per row of the matrix. I think I have the definition here below in in definition 7.1. Oh, sorry, not 7.1. Let me see if I define elementary row operations. Yeah, sorry about that. I didn't define what elementary row operations are because I'm assuming that my students know elementary row operations at this point. By the way, this is my lecture materials for AMAT for Math 175, which is numerical analysis 2, usually taken by math and applied math majors after their linear algebra. Though linear algebra is not a prerequisite, it's safe to assume that my students in this course already took linear algebra. That's why there's a lot of linear algebra stuff that is assumed to be already known to the students, right? So if there are some terminologies not clear in the discussion, just let me know. You can send me an email, or you can just Google it, pause this video, and then Google it so that you can keep pace with the lecture. But otherwise, I'll try to define everything here in the lecture. Okay. Now, all right. So yeah, I'll do elementary row operations. What are the rules, or what are the elementary row operations? There are three types of elementary row operations. Number one, I can interchange rows. Second, I can add to a row a multiple of another row. All right. So interchange rows, add to a row a multiple of another row. And the third one is to multiply a row by a non-zero number. Right? So those are the three elementary row operations. Now, yeah, I'll just do this quickly because this is supposed to be a review of your linear algebra. But the first thing I want to do is to eliminate this guy and to eliminate this guy, right? Because again, my target is to write this as an upper triangular matrix. That means everything below the main diagonal should be turned to zero using elementary row operations. Now, the usual way to do it, or the traditional way of doing it, is to eliminating column by column, the unwanted non-zero numbers per column. So I'm going to start with the first column. I want to make this a zero and this a zero through elementary row operations. So what I'll do to carry this out is first, I will replace row 2, and this would be the notation that is used all throughout this module. So I will replace row 2, so R2 stands for row 2, will be replaced by, all right, this would be row 2 minus 3/2 of row 1. So essentially, this elementary row operation adds to a row or adds to the second row a multiple of the first row. All right. And the goal is to make this equal to zero. That component, the entry on the second row first column to be equal to zero. In order to do that, I need to add to the entire second row, okay, component-wise, negative 3/2 times the first row. So I'm adding to the second row a multiple of the first row, right? So it's going to be 3 plus negative 3/2 times 2. So that's 3 minus 3. So we'll have, so by the way, the first row will be unchanged. Because at this particular step, I am just replacing the second row by this guy. All right. So I'm replacing the second row by the second row minus 3/2 the first row. The second row minus 3/2 times 2. 3/2 minus 2 is going to be negative 3. 3 minus 3, that's going to be a 0. But I'll do this for all entries of the first row. So for this guy, for that entry, I'll have 1, which is that entry, minus 3/2 times this entry. Okay, so that's going to be what? 1 minus 15 over 2. So that's going to be negative 13 over 2, right? So I hope I'm doing my algebra right. So you can correct me if I messed the algebra up, but hopefully I didn't. All right. And then you can also check this entry. Okay, let's do this this third computation. So the entry for this one would be this guy. That's the original entry from the second row, but it will be replaced by the entry minus 3/2, the one above it, the one from the first row, right? It's going to be negative 2 minus 9/2. So that's going to be negative 13 over 2 again, right? That means this will be negative 13 over 2. And you can check that, oh, sorry, I don't have the number yet, but the last one would be, this one will be negative 1 coming from here, the original entry from the second row, minus 3/2 times the entry from the first row. So that's going to be negative 1 minus 3/2, so that's going to be negative 5/2. Oops. Okay. And then you can check that the other entries, or the first 3 entries in the third row would be 0, 0, and sorry, not 0, 0. Okay. Actually, we don't know what will happen to the third row. I'm getting a little excited here, right? But again, my goal is to make this a 0, right? So I will replace the third row by the third row plus, right, a multiple of the first row. Okay. So the first row has a leading 2 in it. I want to eliminate -1, so I need to think of what should be added to it so that this will become 0, right? So the target is this to be 0. So I need to think about what should be the multiplier, what should be the scalar to be multiplied to this entry, right? So that if I add the product with this guy, the answer will be 0, right? And the answer would be what? It would be positive 1/2 R1. Because if you do so, this entry over here, the new entry, will be computed as the original entry. So that's -1 plus 1/2 times that entry in the first row, which is 2, right? So we'll have -1 plus 1/2 times 2. That's going to be 0 as desired. Right? Okay. Then you do this also for the remaining entries, all right? So the third row will be replaced by 1/2 times the first row. So I guess what will happen here? This will be 2 plus 1/2 times 5. So that's going to be 2 plus 5/2. So that's going to be 9/2. And then lastly, we'll have 1 plus 1/2 times 3. So that's going to be 5/2. Okay. And then here, we'll also work the augmented part here. So we'll have 0 plus 1/2 times this entry. So that's going to be 1/2. All right. So I hope I did the math right over here. Okay. And now, okay, we're almost done, except that there's still one unwanted non-zero element. Again, our target is to make this part an upper triangular matrix. For that to be upper triangular, all numbers below the main diagonal should be 0. This is the main diagonal consisting of the entries on the first row, first column, second row, second column, third row, third column, and so on. So all of these guys must be 0, are the diagonal entries. Everything below them must be 0. So we need to make this a 0, all right? And for that to happen, all right, I need to perform another elementary row operation, this time replacing the third row by adding to the third row a multiple of the second row, right? Maybe R3. I hope you get the pattern. This should be -1. Because here I have a 9/2. I want to add to it something, let's call it C for now, times this entry, -13/2, so that this guy will be equal to 0. And then we'll solve for C, right? So here, I guess the answer here is negative. I think the answer is 9/13, if I'm not mistaken. All right, anyway, it's better for us to solve it. So I'll have 9/2 plus C times -13/2 must be equal to 0. So I'll have -13/2C equals -9/2. So C will be equal to 9/13, right? So it should have a plus 9/13 times R2, right? Note that I don't want to add to the third row a multiple of the first row, right? Because if I'll do so, if I'll multiply the second row by something and add to it and add it to the third row, this 0 will be ruined by the multiple of 2. So this will change, which I don't want because I want this to be fixed at 0. So that's why I'm choosing to modify the third row by adding to it a multiple of the second row, because anyway, the second row has a leading 0 already, right? So now what we'll have here, you can check. I'll have 253, and then 0, -13/2, -13/2, 0, 0, and then I'll have a -2 over here. Okay. And then here, 253 and 0, -13/2, -13/2, 0, 0, and then I'll have a -2 over here. Okay. And then here, The augmented part will be 1, negative 5 halves, and I think this one will be 0. Okay. And then how do we solve the system finally? Why did I want in the first place to write it as an upper triangular matrix? Well, I wanted to do it so I can do back substitution. Right? Because the beauty of using elementary row operations in reducing your matrix equation is that you're getting an equivalent system, a system with the same set of solutions as your original problem. Remember, this was our original problem, right? So this is its matrix form, and this is the original equation in system form. Now, the use of elementary row operations guarantee that we get a system or a matrix equation that is equivalent to this one. So whatever the solutions to our new system is, that will also be the solution or the solutions to the original equations, right? Now, all we need to do is to write this in system form again so that we can do the back substitution more obviously or more clearly, right? So I'll write it again in system form. I'll have 2x plus 5y plus 3z, and then I'll have, of course, this would be 0 times x. That's going to be 0. So I'll start with negative 13 over 2y minus 13 over 2z equals negative 5 over 2. I forgot the equal 1 on the first equation. And then the last equation will be negative 2z equals 0. Now, look at the third equation. The third equation only involves one variable. So from there, we can easily conclude that z is equal to 0. Right? Now, if z is equal to 0, okay, then what we'll have is this. Negative 13 over 2y minus 13 over 2 times 0 equals negative 5 halves. We'll have negative 13 over 2 times minus 0 equals negative 5 halves. Sorry, I forgot the y. So this will give us y equals 5 over 13. But that's not the solution I intended to have. Maybe let me double check here. So that's not the answer I'm expecting. So here I should have a negative 1 minus 3 halves times 1. So I really have negative 5 over 2. That's that. I think everything is fine. Okay. And so, yeah, I think that's it. We'll have y equals 5 over 13. Okay. And then now we have the values of our two variables. All we need to do is to plug them into here to get the value of x, right? So this is what we call the back substitution. So we start from the last variable, and then we work ourselves up, because since this only involves one variable, we can solve for that for the value of that variable. So we'll have this, okay, and then we can plug the discovered value of that variable to the second to the last equation, which involves only two variables. But since we already knew the value of the third variable, this will be reduced to a single variable equation, as we see over here. All right. So that will give us y equals 5 over 13. And then finally, we can solve for the last variable, or the value of the last variable, by plugging in the known two values to the first equation. So we'll have 2x plus 5 times 5 over 13 plus 3 times 0 equals 1, right? Then we get 2x plus 25 over 13 equals 1. And then we'll get 2x equals 1. 1 minus 25 over 13, which is basically 13 minus 25 over 13. So we get 2x equals negative 12 over 13. I hope my arithmetic is correct. If not, comment down below. All right. Now, finally, so here we get x is equal to negative 6 over 13. So I hope I did the calculations right because I did it before and I think I messed up the equation that I copied from my scratch work. So this is a different problem than what I intended to have. But hopefully I did the arithmetic right. If not, please adjust the arithmetic. But that's essentially an illustration of how we use the Gauss Jordan algorithm, or at least part of it, reducing the, the augmented matrix to an upper triangular matrix augmented by some constants so that we can do back substitution. Right. So what we want to do now is to examine how we can take advantage of this methodology in order to solve larger systems. So this is the Gauss Jordan or the Gaussian elimination method or the Gauss Jordan algorithm in linear algebra. And this is highly efficient and highly accurate. And I think this is one of the most efficient methods to solve a linear system. But even so, it's still very costly. It has order of complexity big O of n cubed. Essentially, the number of operations required in order to get the Gaussian elimination process done is the same, grows the same at the same rate as n cubed. Okay? And if you have 1,000, where n here is the number of rows or the number of columns, if you have a square matrix. So imagine if you have n equals 10,000. So you have around 10,000 rows and 10,000 columns. So that means in order to carry out Gaussian elimination, the process that we just did, we need to have 10,000 to the third number of operations. And that's very huge. And it is not only time consuming, but it is also prone to accumulation of round-off errors. So probably one of application of Gaussian elimination is fine. But if you will use Gaussian elimination repetitively, which is usually the case for data science applications, we need to find a more efficient way of carrying out this process, right? And actually, this is very important because we usually want to solve systems that are iterative in nature, or we want to solve systems of equations successively, right? Now, we can still make do with Gaussian elimination if you're solving systems of equations of the form ax bar equals b1 bar, ax bar equals b2 bar, ax bar equals b3 bar, and so on until ax bar equals b4 bar. Now, why is this why does this occur so frequently in data science applications? Well, you can think of the b sub I bars to be measurements. This is from town C, and this is from town, say town N, right? And then the X bars represents the parameters that you need in your model. So you want to get, say, what's the birth rate, what's the mortality rate, what's the emigration rate, and so on for the particular region. And then you make some random observations all throughout the region, and then you collect them into the right-hand side. And then the coefficient matrix will define what the population dynamics is. So there's a bunch of equations relating the parameters to each other. Now, the question is, which usually occurs in data science problems, is how do you get the parameters? Of course, you want to get as many data readings as possible from a heterogeneous pool of stratified samples, right? But retrieving the best values for the parameters X bar is quite difficult, right? And very costly, especially if you want to do it this way. Well, if the measurements are all known at the same time. So if you know B1 bar, B2 bar, B3 bar, Bn bar right away, you can just do the same Gaussian elimination process or the Gauss Jordan algorithm we just illustrated in the 3 by 3 case earlier, you can just do it this way: A, and then augment to it B1 bar, B2 bar, B3 bar, and B4 bar. Of course, the number of operations will increase. Sorry, the last one should be N. Okay. But this will still be manageable. And I think this will still be of order big O of N cubed, right? Or something like that. The growth in the number of operations is not that huge compared to if you will perform the Gaussian elimination individually, right? And this seems to be a nice fix, right? So you just do the process, but this time you added some more columns, but essentially the process is the same because remember, in a Gaussian elimination method, all that matters would be the reduction of the left part of the augmented matrix to an upper triangular matrix. We don't care what the structure of the augmented part is. So in other words, we are not really restricted by what the resulting form for the augmented part, as long as the matrix A is reduced to an upper triangular matrix, then everything should be fine. Okay. Now, this could be the ideal case or the ideal solution to the big jump or the big increase in the number of operations required to carry out Gaussian elimination. But the problem will arise if we don't know the B sub i's at the beginning. And this is usually the case for some iterative experiments. For instance, okay, you have the system AX bar equals B1 bar, all right? And what if B2 bar depends on the solution to this system, right? So what if you really need to solve this because this process will give you your B2 bar or your next data. And then that will be the next right-hand side that you will feed into your Gaussian elimination algorithm. So this will go there, and then you will get, and then what if just after solving the system AX bar equals B2 bar, that will be the only time that you will get B3 bar, and so on. So there's no way that we can perform this simple fix for the Gaussian elimination, all right? Because here we really need to painstakingly repeat the process one step at a time, and that will be very time consuming, right? So that's why we need to talk about matrix factorizations, because matrix factorizations will allow us to manipulate the matrix A so that computing any system of the form AX bar equals some vector easily and more efficiently. Because what I'll do is to write A as a product of two nice looking matrices, all right? So that any manipulation I do to the coefficient matrix A will help me solve any system, whatever the right-hand side would be, right? And hence the topic matrix factorization. So essentially, this is like writing your matrix as a product of two different matrices, right? So remember, for instance, we have a factorization of real numbers. We want to write 6 to be, say, 3 times 2, right? Or we can also write it as 6 times 1. The same thing goes for matrices. Some nice matrices can be written as a product of two nice-looking matrices. So for instance, our matrix earlier, the matrix A that we had, which is 2, 5, 3, 3, 1, -2, -1, 2, 1, can be written as a product of the matrix 1, 1, 1 on the diagonals, 3 halves, -1 half, -9/13, and then 0 elsewhere. So this is a lower triangular matrix, right? Because all non-zero entries are below the main diagonal or on or below the main diagonal times 2, 5, 3, 0, -13, 2, -13/2, and 0, 0, minus 2. This one is an upper triangular matrix. Okay. Essentially, this is a matrix factorization for the matrix A. I was able to write the matrix A as a product of two matrices. And they are nice looking because one of them is lower triangular and the other one is upper triangular. And this is important because we learned that it is very easy to solve systems with an upper triangular coefficient matrix because all you need to do is to do back substitution. Similarly, if you have a lower triangular matrix as coefficient matrix, that system can also be solved easily because you can just do forward substitution, right? Now imagine if you can write your huge matrix A as a product of a lower triangular and upper triangular matrix, whatever the right-hand side of your matrix is, you can solve the system much easily, right? And that's also the case even if you have an iterative process like this, that you need to solve the system with the same coefficient matrix, but a different right-hand side. If you can write A as a product of a lower and upper triangular matrix, then you can just examine what the value of the right-hand side vector is and use that in the back substitution and the forward substitution, and you can find the solution without ever doing the decomposition or Gaussian elimination another round. Okay, maybe it's don't worry if it's not very clear for you at this particular point how that will help us, but later I'll illustrate how that really helps us, right? Now, our focus first is to find such a decomposition. Such a decomposition, a factorization of the matrix A into the product of a lower triangular matrix times an upper triangular matrix is called an LU factorization, right? Now take note that matrix multiplication is not commutative, okay? So if you have a matrix A and a matrix B, A times B is not necessarily equal to B times A. Sometimes it is, but most of the times it's not. Matrix multiplication is not commutative, so we need to be very careful which goes first, right? In LU factorizations, we want the lower triangular matrix to be the left factor and the upper triangular matrix to be our second factor, right? And if you notice, I'm using the article a to introduce factorizations, right? Because as in factoring scalars or real numbers, there could be more than one factorization for a matrix. Actually, not just factorizations, but the LU factorization is also not unique. A matrix can have more than one LU factorization. So it really depends on the particular form. Okay. But let's take a look at how it is done, right? Now, the concept of LU factorization is very similar to Gaussian elimination, the process that I introduced to you or recalled to you earlier. Now, instead of doing elementary row operations, which seems to be a very lexicographic or a very abstract thing to do, remember, we are interchanging rows. We are multiplying a non-zero scalar to one of the rows. And the third, we are adding to a row a scalar multiple of another row. All right. So those seems to be very artificial operations. But actually, they are not. They are really born out of what we call elementary matrices. So an elementary matrix is a square matrix. And it is elementary because it is the result of applying an element operation to the identity matrix. So remember, elementary row operations can be done to any type of matrix. But if you do the operations matrix, that matrix, right? So for instance, remember the first operation is an interchange of rows, right? Note that this is our notation for interchanging row I with row J. So we're just swapping the ith row with the jth. So this notation means I am starting with the identity matrix, I'm interchanging its ith row with the jth row, and I'll get the matrix E. Then the matrix E, being a result, an elementary row operation applied to the identity matrix, is an elementary matrix. And if such an elementary matrix is obtained by simply interchanging those of the identity matrix, then what we get is what we call a permutation matrix. Okay. Now, second row operation, multiplying a row by a non-zero scalar. Now, in that particular case, so we start again with identity matrix, and we multiply I uploaded a newer version of the file because I asked somebody to type my handwritten notes into this LaTeX file. And I just discovered some typographical errors, not some, but many typographical errors. So I corrected them earlier today, March 7 at around 12 noon before I started the recording. But there's still some that persisted, like for this one. So row I will be replaced by row I, but all the entries in the ith row is by the non-zero constants. And this is just multiplying row I and scalar row operation. And I'm performing it on the identity matrix. I'm going to get the matrix E. That matrix E is an elementary matrix. And for this class, we will call that matrix E our rows, right? A row scaling matrix. And then the third one is adding a scalar multiple of one row to another, right? So in this example, we are replacing the ith row by the ith row plus a multiple of the jth row, right? If I will perform this elementary row operation to the identity matrix, I'm sure to get an elementary matrix by definition. And we will call the matrix E, which as a row translating matrix, or simply a row translator. There might be some delays in my screen sharing, but I hope it will bother some. Okay. So let's take a look at some examples. Example 7.1. So you have there the matrix E, and if you compare it to the elementary or to the identity matrix I4, the 4x4 identity matrix. So you have ones in the diagonal and zero elsewhere. That's the identity matrix I4. And if you compare it to the matrix E, you see that the matrix E is simply I4 with the first and what? With the first and third rows interchanged, right? So this row is interchanged or is swapped with that row. Okay. So since matrix C is a product of an elementary row operation, particularly interchanging of rows, we get an elementary matrix, and the matrix C is a permutation matrix. Okay. Yeah, this should be I4, another typo. I'll correct all of this later again. Okay. Now, look at this. I'm experimenting here, or trying to multiply or pre-multiply a matrix A, which is given here. So we have a matrix A over here, and pre-multiplying it with the elementary matrix E. And look what will happen, right? So I hope you remembered how to multiply two matrices. So if I do matrix E, this guy, times the matrix A given here, all right, I'll get this. And what do we notice? Note that the first row here now appears in the third row, right? And the third row here now appears in the first row. All other rows remain intact, right? So essentially, the lesson here is, okay, the elementary matrix E, right? This matrix E is formed by interchanging the first and the third rows of the identity matrix I4. Now, if I multiply a matrix A by that matrix E, again, I'm doing multiplication, meaning the elementary matrix E is on the left, while the matrix A is on the right. So this could be described as multiplication of the matrix A by the matrix E. So E is a multiplier to the matrix A, all right? So, and then you see the effect of that multiplication or that multiplication by the elementary matrix. It's as if the elementary row operation of swapping the first and the third rows was done on the matrix A. All right. And essentially, this will happen for all elementary matrices. You can easily see the pattern and realize that whatever was done to the elementary matrix, or sorry, whatever was done to the identity matrix to come up with an elementary matrix E, right? So you start with the identity matrix I sub n, you perform elementary row operations to it to get the elementary matrix E. Now, if you multiply any matrix capital A with an elementary matrix, of course, analytically, you're going to get a product. But that product will be the result of the same elementary row operation performed on the identity matrix to get the elementary matrix E to get the product. Right? So essentially, that's what will that will be the case for any particular elementary matrix. So essentially, what I'm trying to point out here is this, or the seemingly abstract action of elementary row operations to matrices is nothing more but the result of multiplication by an elementary matrix to another matrix. Okay, so maybe another example. So we look at the matrix F in example 7.2. So we have here this guy. Okay, and then if we compare it to the identity matrix I4 again, so this is I4 again, once on the diagonal, 0 elsewhere, you see that the only difference is that the second row was multiplied by -1. And actually, we can obtain F, the matrix F, by performing an elementary operation to I4, which is basically multiplying the second row of I4. So essentially, our action was to transform I4, change its second row to -1 times the second row, right? So basically, we scale the second row of the identity matrix by -1. So that means since F is the result of this elementary row operation applied to the identity matrix, then F is really an elementary matrix. And since it is the result of this elementary row operation, we say that F is a scaling matrix. Okay? And so, if we will multiply the matrix A we have here, so we have here the matrix A, I multiply it by the matrix F, so I'll have F times A. You can do the multiplication by hand, so you carry out this guy times this guy. Again, make sure you have the right order. F is the first factor, A is the second factor, and then perform the calculation. I bet that you'll get 4, 3, 2, 1, -3, -4, -3, -2, 2, 3, 4, 3, 1, 2, 3, 4. Okay, because I know that the multiplication of an elementary matrix is simply, or will simply, give us the result of applying the same elementary row operation done on the identity matrix to get the elementary matrix to get the product. All right. So here, matrix F was obtained by multiplying the second row of the identity matrix by -1. So when I do F, that elementary matrix times A, all I need to do is to perform the same elementary row operation, that is multiplying the second row of my target matrix by -1. So again, now matrix multiplication, elementary row operations are not just lexicographic operations, but they are legitimate operations, which is basically pre-multiplication by an identity matrix, right? So I hope that's clear. Okay, so how about this guy, right? So E1. E1 again looks like the identity matrix, except that I have a -3/4 here, which is not on the identity matrix. But again, you could have started with a 4x4 identity matrix, replace its second row, right? So this is our identity matrix again. Look at the second row. That's the only one different from this guy, all right? But the new second row, or the second row of E1, can be obtained by replacing the second row of the identity matrix by the original second row minus, is it -3/4? I should have had a +3/4 here. So I think this should be plus. Okay. So I'll have R2 plus -3/4. R1. So I will multiply R1 by -3/4 and add the result to the 0 here. So I'll have -3/4 over there. Okay, so that should be plus -3/4, right? So indeed, E1 is an elementary row operation. In particular, it is a row translator. So we're translating the second row by a multiple of the second row. Okay. So I hope that's okay. And if we will perform E1 times A, again, you can now do it two ways. So you can just perform usual matrix multiplication. You know, E1, you multiply it to A, the usual matrix multiplication thing you learn in your basic linear algebra. But since we know that E1 is an elementary row operation, all right, which translates the second row by -3/4 times the first row. So we know that all that will change, or we can perform the same elementary row operation to the matrix A that we had been dealing with since earlier, all right? So you perform the same elementary row operation here to get the product, right? So that's the second way. So we know that the second or the first, second, and the third rows will remain unchanged. Essentially, you start with A. Okay. You perform second row, replaced by second row, -3/4 times the first row. You're going to get E1 times A. Okay. I hope you get the idea now. So elementary row operations are nothing more but pre-multiplication by elementary matrices. Okay. And this will play an important role when we try to get an LU factorization for a matrix A, right? Okay. Now let's try to look at the Gaussian elimination process once more, right? But this time I'll just do it with the matrix A again that we have from above. And again, if you're doing Gaussian elimination, we want to reduce the matrix A into an upper triangular matrix. And we will perform elementary row operations to do that. Again, the process, we can retain the top row. We won't change anything about it because all that matters is the main diagonal, or all numbers below the main diagonal should be turned to zeros. That's what we want to happen. Now, again, in order to do that, we do this systematically. And the systematic way to do it is to work column by column. So we need to work this elements out, we need to reduce them to zeros using the first row, right? So here are the steps that I'm going to do. I will replace the second row. Let me just enlarge it. I will replace the second row by the second row minus 3/4 of R1. Why did I pick that? Because if I'll multiply this entry of the first row, remember that's R1, multiply it by negative 3/4, I'm going to get a negative 3. If I add that to 3, I'll get a 0. That's fine. And I guess we have accomplished our first mission, making this entry or this entry equal to 0. Okay? But you do that for all the numbers. So this guy minus 3/4 times 3 will give you 7/4. This guy, the original entry in the second row, minus 3/4 times 2 will give you 3/2, and so on. Okay, so that's what this elementary row operation will do. Next, we want to change the third row so that this entry, this leading entry 2, will become 0. That's our target. How do we do that? Well, take the original second row, subtract from it 1/2 of the first row. So we'll have 2 minus 4 times 1/2. So we'll have 2 minus 2. So we'll get a 0 over here. And so on. And then the last one, the fourth row will be replaced by the fourth row minus 1/4 of R1. And we'll get this once again. Okay? And we're done with the first column, right? So the first column is fine. Now we go to the second column. Now remember, this is now our main diagonal. We want all numbers to be, or below the main diagonal, to be equal to 0 so that we get an upper triangular matrix. So we need to now change the third row and the fourth row, right? So those are our target rows. Now, in order to make these two guys equal to 0, I won't play with the first row anymore, because adding to these two rows a multiple of the second row will ruin the zeros we already placed in the first column, right? So my only choice for the translator would be the second row. I'll use the second row so that this 3/2 will become 0 and this 5/4 will become 0. And performing your usual algebra will tell us that R3, the third row, can be replaced by the third row minus 6/7 of the second row, right? So that means this guy, 3/2 minus 6/7 of 7/4 will give me a 0. So this guy is now 0. Okay, and you do the computations for the other two columns. Okay. And then the fourth row can be replaced by the fourth row minus 5/7 of the second row. Again, it's going to be 5/4 minus 5/7 times 7/4. We're going to get a 0 over here. So these two elementary row operations will turn this matrix to this matrix with the desired characteristic that all entries on the second column below the diagonal, these two guys, are both equal to 0. Okay, so I hope the process is getting clearer and clearer to you guys. Now, we only have one problem. We're already here. But again, this is our main diagonal. I want all entries below it to be equal to 0. So I have a problem with 10/7. Now I need to change this particular row. Now, if I want to change that row, I will look not on the first row, because adding a multiple of it to the fourth row will just ruin the two zeros we already set up earlier. The same thing will happen if we work with the third row. So our only option is to work with the third row. So we need to look for the number when multiplied to 12/7, then added to 10/7 will give us 0. The answer is 5/6. So you can check that 10/7 minus 5/6 times 12/7 will give us a 0. And you do it to 5/3. And you do it to 20/7, and then you're going to get 5/3. And now you can check it's an upper triangular matrix, right? And hence you get the matrix C. Okay. So essentially, the Gaussian elimination process, or the Gauss Jordan process, reduced the matrix A via 1, 2, 3, 4, 5, 6 row operations down to the matrix C, okay, which is upper triangular in nature. Okay. Now, remember, our goal is to have an LU factorization. It seems that we already have factor is. Or is there a way that we can use the information we got from the elementary row operations in order to get the lower triangular factor? Because this is already our U. All we need to find is our L. Okay. Now, in order to do this, I just need to form the out of this elementary row operations, right? Remember, R2 being replaced by R2 minus 3/4 R1 will give rise to an identity, to an elementary matrix, right? So you copy this elementary row operation, you perform it on the identity matrix, you're going to get E1, which is this E1 that we have earlier, right? So that means that's our E1. Okay. And then copy the second operation, R3 replaced by R3 minus 1/2 R1. Perform that on the 4x4 identity matrix. You will get this guy. Okay. And this guy is an elementary matrix because it's the product of performing an elementary row operation to the identity matrix. Let's call this guy our E2. And then same thing. Let's do the same thing for the third elementary row operation here. Do that or apply that to the 4x4 identity matrix. You're going to get this guy. Let's call that E3. Okay. And then you can check that E1 or that E3 times E2 times E1 times A will give us this guy, which is exactly the same as this guy. Okay. Because it's as if we're just performing all the elementary row operations in succession with each other. So the result will be just pre-multiplication after pre-multiplication after pre-multiplication of an elementary matrix, right? So that's why, yeah. Remember, E1 times A will just perform this elementary row operation on A, okay? Then the result will be applied or will be pre-multiplied by E2. So that means this elementary row operation will be performed on E1 times A, and similarly for this. And again, I hope you see the equivalence now. So pre-multiplication of an elementary matrix will perform or will result to a matrix that is the product of the elementary row operation. Okay. So instead of looking at this operation to be the product of the seemingly lexicographic pre-multiplication of an identity or of an elementary matrix to the matrix A. Now, note that these three matrices or these three elementary row operations are independent, right? Because this only changes R2, this only changes R3, this only changes R4. So in essence, they are independent from each other. So we can place some leeway in arranging them in the pre-multiplication. So E3 times E2 times E1 times A would be the same row operations after one another. But that only applies per level, all right? So we cannot mix these elementary row operations with this guy, right? Now we can continue the process, all right? So this elementary row operation could be our E, what? This could be my 5, and this could be my E6. So 6 elementary matrices coming out of 6 elementary operations needed to be performed to reduce the matrix A to upper triangular matrix. Okay. So in essence, the matrix U was obtained by pre-multiplying the matrix A by E6, E5, E4, E3, E2, and E1. Now in exercise 7.1, I asked my students, and you can also do this as a quick exercise, multiply this out. Write a program or use your computing software, be it Mathematica, be it Symbol Lab, be it Wolfram Alpha, be it MATLAB. You have the matrices E1 to E6. Try to multiply them out, and I bet you will get. I think you'll get you'll get a lower triangular matrix, right? If I am not mistaken. Hopefully, I'm not. All right, and then you multiply it to A, you're gonna get the upper triangular matrix U. This guy. Okay. Again, illustration of the equivalence of elementary row operations and elementary matrices. Okay. Is it too much to handle in one sitting? I hope you already brushed up with your linear algebra before watching this recording. All right. But if not, take it slowly. That's another reason why I wanted to record this first session, so that you get acquainted again with linear algebra. If you're having troubles uh, following through the lecture, then you can pause the lecture, or you can rewind and watch those parts that you are having difficulties with, and then before you move on to the next part, right? When we meet live, we will be meeting live on Friday. Sorry, on Thursday rather. I'm gonna discuss another type of factorization, or I will continue the lecture because I'm also feeling tired already talking and recording this video. So I might take a breather and then we'll continue on Thursday discussing this book. All right. Okay. But again, the problem is how do we get, or how do we get the LU factorization more efficiently, right? Because here, okay, we had a nice way of expressing the entire Gaussian elimination process as a multiplication of matrices, right? So we have this entire Gaussian elimination process, all right, being expressed as matrix multiplication, right? Now, how can I get out of it an LU factorization for the matrix A? Okay. And that's what we'll try to do now. Well, of course, as I mentioned, if you try to multiply this guys, E6 to E1, I guess you will get a lower triangular matrix. I hope I'm right. I have a theorem later. I can verify the statement later, but I think you'll get a lower triangular matrix. And that will give rise to our matrix C, right? Now, to get this product more easily, right? Hold on, let me see. Or maybe I'll do this next time, right? So you have E6, E1, E6, E5, E4, E3, E2, and E1, right? Now I want an LU factorization. So my candidate, because again, my goal is to get A equals L times U. We already have the U. And then from this equation, I'm thinking of writing it as A times E6, E5, E4, E3, E2, E1 inverse times U. But there's a question mark here because I don't know if this matrix is invertible. All right. Is the product of E6 to E1 invertible? We don't have any clue right now, right? But I will reveal a theorem later or on Thursday that will tell us, yes, that inverse exists. Now, if that inverse exists, then there's a theorem in linear algebra that tells us that the inverse of a product is the product of the inverses, but in the reverse order. So maybe I'll put that here. Recall that AB inverse equals B inverse times A inverse if all inverses exist. So if all of the inverses here exist, then the inverse of A times B is equal to the inverse of B times the inverse of A. Okay, so that's the rule in linear algebra. Or in general, this also works if you have multiple factors inside the inversion. So you simply reverse the order and put an inverse to everything, right? So again, keeping our fingers crossed and hoping that all of the elementary matrices are invertible, I can simplify this as E1 inverse times E2 inverse times E3 inverse times E4 inverse times E5 inverse times E6 inverse times the matrix U, right? If all of the inverses exist. If that is the case, then now I am hoping that this guy is lower triangular and this guy is upper triangular. Now, will that be the case? Luckily, everything, all the questions I posed earlier are answered in the affirmative, right? Thanks to the following theorem, right? First theorem, elementary matrices are invertible. So meaning E1, E2, and E3, E4, E5, and E6 are all invertible, meaning all of their inverses exist because all of them are elementary matrices. So we're good. Second theorem, the product of two unit lower triangular matrices is also unit lower triangular. Again, I need to define what a unit lower triangular matrix is. A lower triangular matrix is unit lower triangular if all of the entries have magnitude equal to 1. Okay. So if the diagonal entries are either plus or minus 1, then your elementary matrix or that matrix is unit lower triangular. So for instance, this matrix 1, -1, 1, -1 is unit lower triangle because all of the diagonal entries are of magnitude equal to 1 and all entries above the main diagonal are equal to 0. Another example will be this 1, 1, 1, -1, 3, 0, 1, 5, 4, 3, then all zeros here. This is also unit lower triangular because it is lower triangular and all the diagonal entries are either plus or minus. Okay. Now, since we perform row translations, let's look at our matrices again. So this is our E1. Where's our E1? Yeah, there we go. That's our E1. It's unit lower triangular because everything above the main diagonals are 0. The main diagonals are the main diagonal is composed only of ones. So this is unit lower triangular. E2 is also unit lower triangular. All ones, zeros above. All ones, 0 above. So E3 is also unit lower triangular. The same as E4, E5, and E6. All of them are unit lower triangular matrix. So that means the product, remember theorem 7.2, the product of two unit lower triangular matrices is also unit triangular. So this is unit triangular times unit triangular. So the product is unit triangular. This product is unit lower triangular times E4. That's going to be unit lower triangular and so on. So that means this entire thing, the product, is unit lower triangle. Okay. Then theorem 7.3 tells us that the inverse of a unit lower triangular elementary matrix is also a unit lower triangular elementary matrix. So that means, again, let's have everything here again. So we know that the E sub i's are all elementary matrices. They are unit lower triangular. So since they're unit lower triangular, by theorem what? Theorem 7. By theorem 7.1, they are all invertible. So that means E1 inverse, E2 inverse, E3 inverse, E4 inverse, E5 inverse, and E6 inverse all exist. Since they all they exist because the E sub i's are all elementary matrices. Not just that, they are unit lower triangular. And we were told by theorem 7.3, the inverse of a unit lower triangular matrix is also a unit triangular elementary matrix. So that means E sub 1 inverse is lower unit triangular elementary matrix. E sub 2 inverse is again unit lower triangular elementary matrix until E sub 6 inverse. So each one of these guys are unit lower triangular matrix. But we have theorem 7.2 telling us that the product of two unit lower triangular elementary matrix is also unit lower triangular elementary matrix. So the product of these 6 matrices is also lower unit triangular matrix and hence is an appropriate choice for the matrix L. Right? So I hope you see how all of those things come together. Or am I the only one excited and amazed by everything that I talk about the past 90 minutes or so? All right. So I hope you got the idea, right? So here, so essentially what we got here is we used Gaussian elimination in order to reduce the matrix A to an upper triangular matrix. And it turns out, if I trace all the elementary row operations that I needed or that I employ to reduce A to an upper triangular matrix, I'm gonna get a bunch of elementary matrices, right? E1 to E6. If I will invert, or if I will get the inverse of the product of all those elementary matrices, I'm gonna get a lower triangular matrix, right? In this particular example, right, once you have carried everything out, do I have the answer here? Unfortunately, I don't, right? But essentially, or maybe I'll show it to you next time when we meet live, right? So, yeah, I just want you to take away from now. So you have a matrix A. We can do Gaussian elimination in order to reduce it to an upper triangular matrix U. This is like what we did here. The final output here is our upper triangular factor. But how do we get the lower triangular factor? We translate the elementary row operations to elementary matrices and get the inverse of their product, right? So the inverse of their product would be E1 inverse times E2 inverse times E3 inverse until E sub 6 inverse. And by a combo of theorem 7.1, 7.2, and 7.3, we are assured that that product is a lower triangular matrix. And not just that, it's a unit lower triangular matrix, which is appropriate as our choice for the first factor, which is lower triangular. Now, you might be scratching your heads, not just because we did a lot of things in one sitting, right? But okay, if that's the case, then it is still not efficient to get that lower upper triangle, LU factorization, because I really need to do the Gaussian process for the matrix to get the matrix U, and then retrace what are the elementary row operations to give us the upper triangle, the lower triangular factor, right? Or the L factor in our matrix. Now, what we'll do next time is I'll show you a nice way of, or an easier way, a more efficient way of computing the LU factorization, starting with basing the matrix L or deriving the matrix L in that particular factorization based on the factors or based on the multipliers of our based on the multipliers of our row translators, right? And so that you don't have to go through the tedious process of computing this problem. Because once you have considered, or once you have the row operations, you can just harvest the different coefficients, the different C's that you got from the elementary row operations to get the lower triangular factor. So what I'm getting at is, for instance, do we have that example earlier? Let me see. Did I erase that one? Oh no, right. So remember here, we have the matrix A equal to 2, 5, 3, 3, 1, minus 2, negative 1, 2, 1, right? And then I have a bunch of elementary operations, actually 1, 2, 3 of them, right? So this will give us E1, this could give us E2, this will give us E3. So all we need to do is to take E1 inverse times E2 inverse times E3 inverse to get the lower triangular factor, right? But that is sometimes cumbersome to do, especially if you have lots of factors. Imagine if you needed 100 elementary row operations to reduce the matrix A to to an upper triangular form. That would be very hard, right? But I will teach you the trick next time or next meeting so that here I can have the LU factorization this way. I'll just copy this factor, the upper triangular part, the result of the Gaussian elimination. Duplicate that, copy that here. That would be my U factor. And then the L factor can be discerned directly. Actually, I'll be spoiling myself now, all right? I hope you don't mind spoilers for the next session, right? What we get is a lower triangular matrix. Sorry, not just a lower triangular matrix, but a unit lower triangular matrix. So we'll have a 1 here, a 1 here, a 1 here, because it's a unit lower triangular elementary matrix. And then we have zeros on top because it's it's lower triangular, right? So all entries above the main diagonal must all be equal to 0. Now, what would be the entry on the second row, first column? Second row, first column. Oops, I needed a negative 3/2 here. The trick is you will have a 3/2 here. I hope you can see the pattern. This is the entry on the second row, first column. Second row, first column, I have a negative 3/2 here. I have a 3/2 as that entry. All right. Now, this guy. This is the entry on the third row, first column, right? Third row, first column. I have a 1/2 here. So what would be your guess for the entry here? Okay, so I hope you guessed negative 1/2. And then finally, this is the entry on the third row, second column, right? Third row, second column. I have 9/13. So here I should have a negative 9/13. And here's our L factor. Here's our U factor, LU factorization, right? So we got an LU factorization. So next time I'll reintroduce this shortcut so that you don't have to compute the product of the inverses of all of those elementary matrices. There's a shortcut. And what we get is a unit lower triangular matrix times an upper triangular matrix. The LU factorization, if it exists, is not unique, right? So there could be several LU factorizations for a certain matrix. Now, we will also look at another kind of factorization. I think this one is called the Doolittle factorization, wherein we have a lower unit triangular elementary matrix as our L and an upper triangular matrix. Another LU factorization would be a factorization wherein the diagonal entries are all one in the upper triangular. So we'll have a lower triangular matrix times a unit upper triangular matrix, and that's what we call a Kraut factorization. All right. So if you browse through the modules, so you already read about those names, but if not, don't worry, we'll tackle this again or we'll tackle the rest of the module on Thursday, right? So if you have any questions about the discussion today, don't hesitate to send me an email to clarify things. If I did some silly arithmetic errors, just tell me via email so I can correct them on Thursday, right? This is already recorded, so I won't be able to go back and edit that particular part. So I'll just make a formal erratum or errata on Thursday, but hopefully everything is well. You got everything that you need from today's lecture. If not, you can watch this on demand, all right? The beauty of recordings, right? So you have access to this on demand. If you have some questions, if something is bothering you, you have a burning question that can't wait until Thursday, send me an email. I'll be happy to walk you through it and answer your questions or clarify some things. But other than that, we'll see each other live on Thursday. We'll use the Zoom details for the rest of the discussion about this module, right? It's I think we only have probably 30 minutes left for this module, and probably I can start another module which will be about either the QR decomposition or I can go to the Moore-Penrose pseudo-inverse. I'll just count how many days I have left for this unit, and based on that, we'll I'll decide what would be our discussion points for Thursday, right? So thank you guys for watching the video. I hope you got something. Let's see each other again on Thursday, all right? Bye, guys.